Welcome to today's video. We are going to be looking at your wave test 2 feedback. Alright, now feel free to skip the video and only focus on the part which you got wrong. Now, the first question is very important. So in order for you guys to get 6 marks, let's take a look how we can get this done. Now, this figure here is showing a beam of red light. Okay, so we've got red light here. So this here A is red, and you've got this one here red as well. So approaching one side of the rectangular cube. Okay, and the beam of light would pass through the block and leave through the opposite side. So it's going to go through this block of glass and then it's going to leave out. Now A and B is a wavefront. Now we know from when we did wave, we know that the wavefront is pretty much, if you're looking at the wave from the top, okay, so you just see the peaks and the bottoms. So these are pretty much the wavefront. So here, this line here, that's the wave. Okay, so this is the wave coming up. So normally when you look at the top, you can see only the ripples. So this is like the ripples. Okay, now we need to discuss the path of the wavefront A and B as it enters the block. Okay, now first of all we need to identify which one is more dense, which one is less dense. So air is definitely less dense. Alright, and our glass is definitely more dense. Okay, now it's going from a less dense to a more dense medium. So we need to talk about what will happen to the ray of light. So A and B, what will happen to A and B when they go through it? And finally, what will happen when it leaves? Okay, for 6 mark. Now, you can't just say, let's take a look. So first of all, if this here is A, so this point is A, the other point is B. So which one do you think will enter the block first? Okay, so which one will enter the block first? So definitely A will enter first and then B in this particular case. Now, when we talk about this, we need to say the first point. We need to say which one will enter first. Okay, so point number 1, we're going to say A will reaches the glass block before B. Okay, because that's how wave travels. So this part here is the one that will reach the boundary first before B, and what will happen is A is the one that's going to go through it. Okay, so the second point, okay, so A enters the block, okay, and it slows down. Okay, so first of all, A is the one that reaches first, and A enters it, and A will slows down. Okay, slows down in block because block is more dense. That's why it slows down. Okay, so at this point, what's happening at this particular point? Okay, so as A enters, so let me just draw this again. So that A enters, so A is the one that's going to slow down. So when slowed down, it's going to bend. Yeah, but look at B. B is still in the air. So B is still in, so B is still in the air. Okay, so this is the first 3 points which you need to say. Okay, and the last 3 points we just need to talk about refraction in this particular case. Okay, so this causes the wave to refract, you can say bend, okay, in this case, towards the normal. Okay, so this will cause it to bend towards normal. Okay, now let's talk about when it leaves. So when it leaves, A will leave first. So A is the one that will leave first. So here, so it's going to bend towards the normal. Let me draw the normal again. Okay, so ideally you want to use a ruler. So here I'm doing it on my computer, so it's going to be the ruler is not. I don't have the function. Let me just check. Yeah, I don't have the function for the ruler on this one. So normal, it's going to bend away. Carry this on. Normal, bend away. So this here is the normal. Bend away. Okay. Now which one? So it's gonna go, and which one will leave first? A is gonna leave first. So far this spot is A. This spot is A. This spot is A. So when it leaves, so you see A will leave first, and then followed by B in this particular case. So when it leaves, so when the wave leaves, A will leave first in this case. Okay, and the wave will refract away from normal. Okay, and you can also say that A will speed up. Okay, now many of you got when you got marked. For those of you who got marked, and you definitely got marks when you talk about the bending of light towards the normal or away from it. Okay, but the reason why you lost mark was you failed to mention that there are so this here means that they are. So this here means they are uh, at different times. So this means pretty much different times. But we are being more specific in this particular case. So we're saying they are crossing the boundary at different times, yes, but in this particular case, A is crossing it first and then B in this case. So it slows down, okay, in the more dense medium. So this goes to wave more dense medium. So in the block, where the block is more dense in this particular case, okay. So for those of you who lost mark in this case, to make sure that you add this properly. As you can see, I've done 1, 2, 3, 4, 5, 6 bullet points. Okay, make sure that you write it proper pen properly, because we should be able to answer this question next time. Okay, so it's not just about refraction; it's about also A and B. Which one goes first? Which one slows down and speeds up? All right. Good. Now let's move to the next one. So now here we have a diagram. Diagram 1 shows a glass prism. Okay, and what's happening in this particular case? Now, if we look at the light, the ray of light is going in, it bends. However, in this particular case, at this point, instead of going out, what happened? It stays inside. So it's the same thing here. Instead of going out at Q, what happens to it? It stays inside. Now, this means that is TIR, total internal reflection. Now, why is total internal reflection happening in this particular case? Okay, at Q. Why is it happening at Q? Now glass, we know that glass is more dense. And air, so, well, we can assume that it is air. Okay, but it's not telling us which one is it. Okay, but we know there are two conditions. So the first conditions, wave needs to move from more dense to less dense. Okay. Second one is the angle of incidence is greater than, I would say not greater, I would say must be greater than critical angle. Okay, so here, if I remove this, if I draw my normal here, the angle of incidence, so this is angle of incidence. It means that the angle of incidence need to be more than the critical angle. So this way, instead of going out, okay, everything stays inside. So that's what we want. That's what we want. Now the main one, so based on this one, since we are not sure, I think we do, but it's 2 marks. Here are the 2 marks. Okay, we're going to be looking at the mark scheme later on, but just I'm going to go through it with you. Okay, now this one, okay, now mark on the diagram I for angle of incidence and R for angle of refraction. So we have air, so this is less dense, so it's going into glass. So angle, so pretty much we just need to label the angles. So the angle of incidence I is going to be here, so this is I. Okay, because the angle of incidence is the angle, so this here is the incident ray. Okay, how do we know if it is the incident ray? Because it's the one that's going in. So the word incident in means it is going in. That's what, look at the arrow is going in, and this is the glass. So if when it goes in the glass, so this here has to be the refracted one. So refracted ray. Okay, but here we need to label the angle. So what is the angle? So the angle is going to be here. Here you go, R. And that's your 2 marks. Now the angles is always between the normal and the ray. So look where the ray is. This is the ray, and this is the normal. This is the ray, this is the normal. 2 easy marks. Now, which one is correct? So when light, when the wave, doesn't matter what wave, so in this case light, when the wave enters the P, so P, when light enters a more dense medium, what will happen? So what will happen? We know that the speed is going to decrease. Here we go. The speed is going to decrease. That's it. Because it's more dense, so it's going to go slowly. Frequency, nothing happens with frequency. So nothing happens with frequency. It's only the speed that change. Therefore, the wavelength will change. Okay, so speed decreases. Okay, good. Now let's take a look about this one here. Now here we have what we call dispersion. Dispersion. So be white light, so the sunlight, so this is white light. Okay, it goes to the prism will bend it, it's going to refract and disperse, and here look, it's bending when it leaves, and therefore we get this nice spread of colors, red on the top and violet at the bottom. Question is, in terms of refraction or wavelengths, the path taken about the light in this particular case. Now the first mark we need to say is we need to acknowledge, so why are we getting red and violet? Where are these red and violet coming from? So the red and violet are coming from the sunlight. Okay, so we need to say that sunlight slash white light, okay, they consist of a spectrum of colors. Okay, because that's, in order for us to explain the path taken by red and violet, we need to know where they're coming from. So this is the first point. Okay, good. Second point, now different colors will have different wavelength. Okay, different colors will have different wavelengths. So this here will have a different wavelength, this here was going to have different wavelength. Okay, and finally, okay, due to that, they will refract by different amount. Okay, so for example, this one here will have longer wavelength. This one here will have shorter. If you remember, the symbol for wavelength is the upside down Y, so shorter wavelengths. Okay, so that's why this one here, red light refracts least, that's what's on the top, because it has a longer wavelength. Okay, violet has a shorter wavelength, so it refracts more. Now, how do you know it refracts? Refracts just bends. Look, if you draw a normal here, look how much it's bending. Look at this one, not by much. So violet is the one that is bending the most. Okay, so you need to say that the light, white light, consists of spectrum colors. That's one. Okay. Second, that each of these light will have different wavelength, and by having different wavelength, they will refract by a different amount. Now, some of you talk about it being longer and being shorter, so you need to make sure which one's shorter, which one's longer, which one is least, which one will bend the least, which one will bend the most in this particular case. Okay. Now, describe a method a student could develop, okay, to search for evidence that sunlight consists of additional electromagnetic waves with frequencies lower than visible light. Okay, now visible light has all the colors, so from red to violet. So here, this question is asking us, okay, what procedure can someone do to find other electromagnetic wave other than the red all the way to violet? We're not looking at yellow, we're not looking at purple, all the way from red to violet. We're looking for frequencies lower. Now let's take a look at our spectrum. So what we have gamma, we have X-rays, we have UV, we have visible light, we have after visible light, we have infrared, we have microwave and radio wave. So frequency lower than visible light. These are the three ones. These are the three. That's infrared, microwave, and radio wave. So we need to work out the procedure. So procedure, like the step to be taken to find one of these waves. Okay, it's 2 marks. We do not need to talk about all of them. Okay, one is enough. Okay. Now, radio wave. Let me think. Okay, so in this case, how do we know if the sun has radio wave? Okay, could be a little bit complicated. Microwave. Okay, how is that? Infrared. I'll focus on infrared because infrared is pretty much heat, isn't it? Infrared radiation is heat. Okay, and heat, if you stand outside, you can pretty much, what happened? You can heat it up. That's it. So you stick with the easiest one. So infrared is the one we're going to stick with. Now what are we going to do? Okay, a procedure. What procedure can we do to show that sunlight consists of infrared radiations? In this case, we only focus on this one. Okay, what can we do? There's many things that you can do. Okay, you can have someone stand outside in the sun for a few minutes. Okay, 30 minutes, and then how can we check whether he's getting infrared radiation? Infrared radiation has to do with heat, so all you need to do is just measure his temperature, and that's it. Okay, so here we go. Have someone or something. Okay, something, one slash thing. Okay, exposed to sunlight for a period of time. Okay, then measure its temperature with a thermometer. Okay, and increase in temperature will prove that the sun emits infrared radiation or infrared waves. Here you go. That's all you can do. Pretty much just use a temperature to measure. Use a thermometer to measure temperature or something. Okay. Now, if you want to microwave, normally we use it for communication, so it could be a little bit complicated for that. Radio wave, again, we use it mainly for communication. Could be a little bit complicated, so we may need like a device and stuff like that to work this out. Okay, now this one we can also use something called a thermal camera. Okay, now the thermal camera is going to help us see infrared radiation, but how will it help us see infrared radiation? So bright spot is equal to warm, okay, and dark spot is equal to cold, cooled. Yeah, I say cold. Now, if you use, for those of you who said use the thermal camera to work out to find infrared radiation, you need to say how will this work. If you remember when we talk about infrared radiation, I showed you guys the pictures of how the infrared camera work or the thermal camera work. Okay, so the brighter the spot, then the warmer it is. It means it has a lot of infrared radiation. If it's darker, if it's blue or darker, then it means cold, it has less infrared radiation. Okay, these are the two ways in which you can say. Okay, good. Now let's take a look about this one here. So some television use infrared radiation. Others use radio wave. Okay, so we have two, infrared or radio wave. Question here is, why infrared remote control may not switch the TV from behind a armchair, but radio wave works? Now, if you draw a diagram, let's say we have a chair. Okay, let's say the TV is there. Okay, now it's saying here that microwave, M for microwave, nothing happened to the TV. But if we have radio, then it works. Okay, now radio wave has longer wavelength than microwave. Okay, right. Microwave will be absorbed by the armchair. There you go. That's it. That's all you need to say. First of all, it will be absorbed by the armchair, and then you talk about something. You talk about the wavelength. Okay, the wavelength, or you can also talk about frequencies. In this case, this one here is going to has lower frequency than microwave. 2 marks. That's it. See how easy you can get to 2 marks. And the last question. Okay, so microwave is used to send signals to satellite and describe why microwave is used. Now, if you remember, we've got the Earth, we've got the antenna. Okay, you have the layer here, and then you have the satellite. So saying here microwave can easily go. So microwave, M, microwave. Why is that it can go? Now, first mark, microwave is able to go through the atmosphere. That's it. Why do we use it? It's used sense is because it's able to go through the atmosphere. Now, what will happen to radio wave? Now, radio wave goes through the atmosphere, and what will happen? Radio. Now, radio wave will be reflected. Let me just write it properly. Be reflected off by the atmosphere. That's why microwave is used, because microwave is able to penetrate, go through the atmosphere without being, and radio wave is going to be bound, would be the one that get bounced off. Okay. Now make sure that your work is properly in purple pen. As you can see, we need to know how this works. Now I'll show you the mask scheme as well, in case you are not sure. Okay, so this is the mask scheme for the first one. Okay, now 6 marks, these are the bullet points. However, you need to make sure that these bullet points make sense. Now it says here, if you want to get full marks, okay, you need to demonstrate accurate and relevant understanding, well developed and structured. Okay, these are the points. You need to make sure that you start properly and you end properly. So make sure that if you want to take a look at this one here, you pause it, okay, and then you put a pen. Now let's move to the next one. TIR, an explanation linking. Here you go, 2 marks. You get 1 mark for saying angle of incident greater than the critical angle. That's it. Okay, that's it. There's nothing about density. So for those of you who talk about density, unfortunately, I may not giving you a mark. Now the draw. So we need to label the diagram. Okay, we've done that already. That's fine. Speed decreases. Good. Yeah, this is dispersion. So this is dispersion here. Dispersion question. Dispersion. White light is a mixture of different wavelength or different colors. Oh, it says here ignore colors. Okay, look, ignore colors. So we need to go back and check this properly. Spectrum of colors, spectrum of colors, spectrum of wavelength. Okay, now let's take a look. This one here would be plausible because in the next sentence we talk about that these colors will have different wavelengths. So it's pretty much a mixture of wavelengths. So that's fine. So each color is diffracted by different amounts. That's fine. Okay, so even though it says ignore colors here, but the way we have worded it, okay, the way we have structured our answer, we said white light consists of a spectrum of colors, not just a color, and different colors will have different wavelengths. So we already, so in these 2 points, we've already clarified this. Okay, so this should be fine. And each color will be diffracted by a different amount. Here we go. And short wavelengths are diffracted more. Okay, if I go back, and this is something we talk about, so different amount, and I'll link this to here. Okay, so short wavelength will diffract more, refracts more. Okay, so this here goes, so this is also points. Okay, we need to also include this as 1, 2, 3, 4. Okay, good. Here we go. This one here, place a thermometer. Oh, this is the bulb. Okay, beyond the position of red lights. I look at the rise in temperature. That's it. Okay, so place the thermometer near the bulb and look, wait for the rise of temperature. That's it. Okay, and the last question: infrared is absorbed by the armchair, can it go through? Okay, or radio wave go through? So it's all. So 1 mark here, all. This one wave, they have different wavelength or frequencies. Here you go. That's it, pretty much. And the last one: radio wave will not reach the satellite. Okay, they get reflected off. Okay, they're reflected off. Okay, so same thing for microwave. So radio wave will not reach, or you can say microwave will reach. Okay, and radio wave here are reflected off. Here we go. Now, if you finished your bubble pen, make sure that you move on to your revision for your next. You move on to the next part.